I will say a lot of high school, I tried to push myself as hard as possible and I joined as many organizations that I could that I felt passionate about. And I was on a lot of sports teams and I really made it my personal goal to just be as kind and loving to everyone as possible. And I feel that being determined in those values has best prepared me for college because when I got here, I had this confidence to be able to go and meet people and to know what I want and also to drive myself to stay studious and balance soccer and friends. It's definitely possible. You can do it. You just first have to believe in yourself and take a deep breath and go for it. The ability to communicate and to learn how to communicate with yourself and to other people is one of the most important skills to learn in your life, so start in college. With that said, when you learn how to communicate and to read people and to build that level of social skills as well, you're going to become a better leader, and at the end of the day, that's going to excel you into helping change the future. I just want to start off saying you are more than capable of doing anything that brings you joy and brings your life meaning. With that said, I'm on the women's soccer team, I'm vice president of SGA, I'm pre-med. I'm doing everything that helps me feel like I'm contributing to the community. With that said, the way I balance things is I put my self-care first. I have to pour into myself in order to pour into other people. And the ways I do that is journaling. I keep a to-do list, a to-not to-do list, and I look at life with the mindset of I'm going to live life by helping people, by serving other people, because that's what brings me joy. Hey guys, I'm Carol Johnson. I'm a junior biology major at Birmingham-Southern College. I'm excited to talk to you guys about weak acids and bases. To simply describe the difference between strong acids and weak acids, it is that strong acids completely dissociate or break apart their ions, while weak acids partially dissociate. If we look at the picture on the left, we can see a visual depiction of this difference. The acid molecule, to begin with, has a hydrogen molecule attached to a negative ion. When added to a solution with strong acid, you can see that the negative ion and the hydrogen ion completely split apart from each other. However, when the weak acid molecule is in the solution, most of the acid molecules are still together, and some of the hydrogen ions and negative ions are split apart. The picture to the right shows the difference between a weak acid and a strong acid titration. It is important to realize that the strong acid has a lower pH, therefore a more distinct change when a base is added to the solution. However, the weak acid has a higher pH, therefore the pH is not as drastic as a change when the base is added. Let's explore more differences between strong and weak acids. The strength of a weak acid depends on their Ka value. The table to the right is an example of this. You do not need to remember their Ka values because you can find them in your textbook. The table on the left explores more of the differences between strong and weak acids. You can take a second and pause the video if you would like to take notes of common weak acids and information about them. Strong bases are compounds that completely dissociate into its cation and hydroxyl ion in a solution. Although weak bases are compounds that partially dissociate into its hydroxyl ion and cation, thus creating an equilibrium condition. They are also less reactive, have a lower pH than a strong base, and the pKb value is high. The strength of the base depends on their Kb value. The table to the right identifies weak bases and their Kb values. It would be important to remember some of these common weak bases to make solving problems easier. You do not need to memorize Kb values because you can find this information in your textbook. However, some textbooks do not include this information, so to find it you simply do Kw divided by Ka. Kw is a constant always equal to 1 times 10 to the negative 14th. Carboxylic acids are organic acids that contain a carboxyl group attached to an R group. They act as weak acids. Carboxylic acids make up amino acids and fatty acids, which is important to understand when studying the human body. Amines are compounds and functional groups that contain a basic nitrogen atom with a lone pair. They act as weak bases. Above you can find an image illustrating and listing some amines. Let's recall the concept of buffers. They are solutions which resist change in pH upon addition of a small amount of acid or base. A buffer is simply a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. It will be helpful to take notes of these relationships because you will become more efficient when solving acid-base problems and feel more confident in the material. Here are the steps that you can take when calculating the pH of a solution of a weak acid or base. Step 1. Determine the chemical equation when the acid dissociates, or the base. Step 2. Find the initial molarity of one of the substances. Step 3. Fill in an ice chart so you can find the values of the protonated ion and the anion at equilibrium. The I stands for the initial concentration, the C stands for the value it has changed by, and the E is the value at equilibrium. Step 4. Write the equilibrium expression Ka equals concentration of products over concentration of reactants. Step 5. Plug in what you know about the concentrations and the given value for Ka or Kb. Step 6. Use the shortcut method or the quadratic formula to solve for x. Step 7. Once x is found, use pH equals negative log H plus to find the value of pH. Alright, let's practice finding the pH of a weak acid. Determine the pH of a 0.095 m solution of hypochlorous acid. The Ka is 3 times 10 to the negative 8. Step 1 includes finding the chemical equation of the solution when this acid dissociates. As it dissociates, it will remove the hydrogen ion and leave us with a conjugate base ion. Step 2. From the problem, we are given the initial concentration for HClO, and it is 0.095 m. Now, for step 3, we fill out our ice chart. The initial concentration for HClO is 0.095. HT and ClO minus are both 0. We assume as the reaction progresses, the hypochlorous acid will decrease by a factor of x, and the products will increase by a factor of x. These all increase/decrease by the same amount because they all have the same coefficients. Now the equilibrium concentrations will be for HClO 0.095 m minus x. For H, it will be plus x, and for ClO minus, it is plus x as well. For step 4, let's write our equilibrium expression. The equilibrium expression compares the concentration of the products to the concentration of the reactants. Now, for step 5, let's plug in what we know about the values for the equilibrium concentrations, which we will have 3 times 10 to the negative 8 equal to x times x divided by 0.095 minus x. So for step 6, when solving this equation for x, sometimes you may have to use the quadratic formula. However, you can use this shortcut when you compare the Ka value to the initial concentration value, and if the Ka value is drastically smaller than the initial concentration value, then you can assume that x is so small that it is being subtracted from 0.095 that it is basically 0, which simplifies the problem to being 3 times 10 to the negative 8 equals x squared divided by 0.095. Now when solving for x, we multiply 3 times 10 to the negative 8 by 0.095 and take the square root of that, which gives us the concentration of H plus and ClO minus to be 5.3 times 10 to the negative 5th. Step 7, we use the negative log of H plus concentration to find the pH of the solution, which is 4.27. Now, let's practice a problem where we find the pH for a weak base problem. What is the pH of a 0.5 m solution of ammonia? Step 1 includes finding the chemical equation of this solution when the base dissociates. Step 2, from the problem, we are given the initial concentration for NH3 is 0.5 m. Now, for step 3, we fill in our ice chart. The initial concentration for NH3 is 0.5 m. NH4 plus and OH minus are both 0. Now, the equilibrium concentrations for NH3 will be 0.5 minus x. NH4 plus and OH minus will both be plus x. For step 4, let's write our equilibrium expression. So to find Kb, we divided the constant Kw by Ka. So 1 times 10 to the negative 14th divided by 5.6 times 10 to the negative 10th is equal to 1.8 times 10 to the negative 5th. Now, for step 5, let's plug in what we know about the values for these equilibrium concentrations, which we will have 1.8 times 10 to the negative 5th equal to x times x divided by 0.5 minus x. For step 6, when solving this equation for x, sometimes you may have to use the quadratic formula. However, you can use the shortcut when you compare the Kb value to the initial concentration value, and if the Kb value is drastically smaller than the initial concentration value, then you can assume that x is so small and just make it 0. That then simplifies the problem to be 1.8 times 10 to the negative 5th equals x squared divided by 0.5. Now, when solving for x, we get a concentration of NH4 plus and OH minus to be 3 times 10 to the negative 3rd. Step 7, we use the negative log of the OH minus concentration to find the pOH of the solution, which is 2.52. Now we go one step further to get the pH by subtracting the number 14 minus pOH. So here we would do 14 minus 2.52 to get 11.48. Thank you guys for watching, and I hope this was helpful. I hope you have a great day.